And I could pull up, if we wanted to, let me pull up our flip chart from the other day. Maybe this stuff looks familiar. Remember that? We talked about redefining the area under the curve to write it in a convenient geometric shape instead of a curvy shape, right? This is where we brought in our calculus two-dimensional angle grinder, and we just grind the function down, and the rubble spills over and fills in this little gap right here. And when we get down to this point, the rubble is as high as what we've planed down, and it just looks like a rectangle instead of an inconvenient shape, right? And so we know then that whatever the height of that rubble pile is, right, the height of the rectangle, which we're going to call f of c, that's defined as the average value of the function, right? If we reconfigure the area under the blue curve to look like the area under the purple line, right? And so that's the average value we call f of c. And what's c then? Well, c just is the value, the one or more places where the function actually has its own average value on that interval, right? So every place where the function passes through its average value would be a value of c, right? So that's our mean value theorem. So then, what are we going to do? Yeah, there. Okay, so what are we going to do with our problem then? We want to find two things. We want to find what's the mean value of the function on this interval. How are we going to do that? We can just do a quick little sketch if you want to. What's sine x look like from 0 to pi? Yeah, it just looks like just this. And then if we keep going, we just want to 0 up to pi. So what do we do? Integral?
Yeah.
Okay, good.
0 to pi.
Integral from 0 to pi, good.
Sine x.
Okay, good. So what's that mean? What's that represent? The integral of sine x dx from 0 to pi. Area under the curve. Yeah, the area under the sine curve from 0 to pi. Good. So it's going to be all this area right there, right? And then what else are we going to do with that? So that's the area of the function. To find the average value, what do I do? Right. Really, all we're trying to do is reconfigure this, right?
Divide by pi minus 0.
Yeah, divide by pi minus 0. So all we're going to do then is we're going to reconfigure this into a rectangle instead. Right? The width is going to be the same width. The width is just going to be pi minus 0 or pi. But the height is going to be f of c, right? So we know the blue area equals the white area. Okay? So integral f of x dx from 0 to pi equals height times width, right? So if I want to solve for f of c, I'm just going to divide each side through by pi minus 0 or pi, right? So what do we get? Let's do the calculus. We'll review the calculus here. So what's the integral of sine x? Okay, negative cosine x. I can pull the negative out front. We're evaluating that from 0 to pi, right? All divided by pi. Well, what's that give us? So we get negative, I'm going to evaluate this at pi first, right? I'm going to take the difference between cosine x evaluated at pi and 0. So negative, what is cosine of pi?
-1.
-1, good. Minus cosine of 0?
1.
1, good. So that gives me -1 times -2, so I just get 2 over pi. Okay, so there's the average value of the function. Now, what if we wanted to find all the places where the function has that value? Well, that's not a very convenient value, is it? Right? So, I mean, we're just going to set the function equal to 2 over pi and ask the question, where are they equal? And I'm only going to keep the solutions on our interval from 0 to pi. Right? There are going to be an infinite number of those. Sine curve oscillates infinitely, and so we know that if we set that equal to some y value, I'm going to get an infinite number of answers, but I'm only going to keep the ones between 0 and pi. Okay? How we do so far? How we doing this? Is that making sense? Right? Average value of the function is just going to be the area under the curve divided by the width of the interval every time. Okay? So if we do the algebra on this one, then if we set sine x equal to 2 over pi, what do we get for our answers? What's x equal to? So roughly, what's the only way we could write an exact answer here? What'd you do to get that answer? Arc sine, yeah. So we could write this as arc sine of 2 over pi. That's our answer, right? That's our set of answers. We're only going to keep the one of those that falls in our one or maybe even two. I think it should probably be two. It should be two. Yeah, it should be two. The two answers that are going to fall in our interval, right? So if we pull up a calculator, let's just pull up Desmos. And I want to find those intersections. Okay, let's see. So we can do this a couple ways. We can graph y equals sine x. Okay, and we can graph y equals, what was it, 2 over pi? And just look for all the intersections on our interval. To make this convenient, why don't we just go from, we'll go here to the graph settings, and we'll let x just run from 0 up to pi, and then y will let go from -0.1 to 1, how about? Just so we can see this a little better. And there's our two intersections, right? There's one, and there's one. So what are my solutions? 0.69 and 2.45 if we're just going to, provide decimal approximations. Right? Does that make sense? Okay. Okay, got one more for you. Let's calculate. Just want you to think about something. Not that this is going to be a big deal right away, but I just want to start you thinking about this. What if I wanted to find the area between let's say we want to find the area between, let's do f of x equals x squared minus 4x plus 4. and g of x equals let's make that +8. And g of x equals 4. I want the area between those functions on the interval from 0 to 4. Between the curves. How can I do that? But what's this one going to look like? What's f of x?
So we're finding the area between one curve and then the other one.
Yep. What the area between the curves on that interval. Just a little algebra 2 review here. How could I, really quickly, how could I graph that thing?
Just parabola.
It's a parabola, right. If I were to complete the square on that thing, I could write it in vertex form, which makes it really easy to graph, right? So, let's see, I could write that as x squared minus 4x. What's the number that would have to go with those two to create a perfect square trinomial? X squared minus 2x plus what? Yeah, 4. Half of negative 4 squared, right? So that means I would have an additional plus 4 stuck out there on the end, right? You see that? Okay. You know what? I think I messed that up. No, that'd be okay. Yeah, that'd work. Okay. So then so this is x minus 2 quantity squared, isn't it? Right? So we could write f of x if we want as x minus 2 squared plus 4. So where's the vertex of this thing? 2, 4, okay. So we're going to go over 2 and up 4. And then it's just a normal looking parabola, right? Because a is equal to 1, right? So we know that I'm not stretching, I'm not dilating it vertically at all. So we would just go over 1 and up 1, over 1 and up 1, over 2 and up 4, right? So it's going to look like that kind of a thing. And here's this line, right? So what's the area look like that I'm trying to find it? If we're looking only on the interval from 0 to 4, we're going to start adding up area there and stop adding up area there. We want the area between the curves. So you see that it's going to be that area and that area. How can I do that?
And you could just find the area of both and the difference.
Oh, okay. So I could find the area by subtraction here, couldn't
You could also find the average and just use g of x as your x-axis.
That's, you know, I'm not, I see what you're getting at there, but if that works, that's going to be complicated. What you said the first time is really the best answer, right? All we really want to do, if I want to find that blue area, couldn't I think of that as being the area under the white curve, right, which is going to look like it's that whole thing minus the area under the yellow curve, right? Everybody agree?
Which is just the blue area.
Which just leaves us with the blue area, doesn't it? Right? So the whole area under the white graph minus the whole area under the yellow graph gives us back the area that's left over, right? So really this is no big deal. If we set this up, if we want to find the yellow area, I'm just gonna have, how do I write the area under the white graph?
4 over 0, 4.
Yeah, so it's gonna be integral from 0 to 4 of, well, just that, right? Just f of x. Might as well leave it. Now, if I'm integrating, that's not a really convenient way to do it, is it? In that case, if I'm anti-differentiating, right, if I'm just trying to play calculus Jeopardy, I'd much prefer to just have a polynomial, right? So I've got the integral of x squared minus 4x plus 8 minus the integral of what? 4. Yeah. Right? Now I could, very easily, I could just add up both of these areas and subtract them. Let's do that on Desmos. I just want to make one more little point with this. I just want you to kind of get you back. Been gone for a week, hoping you didn't do a lot of schoolwork. You just got a chance to relax a little bit. But now we're kind of back into it. So if we want to add up the area under, I can't remember how the heck do you do this in here. I can't remember. This would be a good thing to kind of figure out together here real quick. You guys done integrals on Desmos? Okay, I know there's a pretty slick way to do it. Right there. Good. So we do integral from 0, isn't this cool? 0 to 4 of
X squared minus 4x plus 8.
minus 4x plus 8 dx. Okay, so it gives it to us. And then down here we can just do integral. What does that show up like? I'm just curious if I go. Oh, it doesn't show us anything on the graph though. Gives us an answer though. And then down here we got the integral. They're just under miscellaneous on functions. Integral from 0 to 4 of 4. That gives us 16. So let's define that as A1. And this is going to be A2. There's our answer, right? Okay, so 5 1/3, 16/3, what we get if we did the math. Okay. Could we use properties of integrals to simplify this before we actually did the calculus? This is what I want you guys to start kind of seeing this in terms of. So if I've got integrals over the same limits, right? I've got the integral from 0 to 4 of f of x dx minus the integral from 0 to 4 of g of x. What could I do?
You just combine them.
Yeah, I could combine integrands, couldn't I? Did everybody see that? Because all this stuff is the same. Everybody see that? I should be able to just say this is equal to the integral from 0 to 4 of that stuff minus that stuff, right? which is what?
X squared minus 4x plus 4.
Now that's kind of interesting because look what that, if I were to graph, let's just graph the functions for a second here. I just want you to see, just get an appreciation for this. This stuff that just still, this fascinates me that calculus does this for you. So let's call this f of x. So there's f of x, right? Here's g of x. Okay. Well, there's h of x. So the area between the orange and purple graphs is the same as the area under the black graph. Now we can see that because the purple graph was linear, that just amounts to a translation, doesn't it? Right? But what if we tweaked g of x, so instead of being 4, it's something like 4x? Look what that did, something completely different, right? So the area now between the orange and the purple is the same as the area under the black graph, and now the black graph looks completely different, right? So we're reconfiguring that area. Just ponder that a little bit. What's that? We said h of x is just f of x minus g of x, so it's the area underneath the orange graph and on top of the purple graph. So right here, that's going to be positive, isn't it? Because the orange graph is above. But over here, if the orange is defined as the top, now we're adding up the area backwards, right? And so we're end up getting a negative area. Another way to think about that is the area under the orange graph minus the area under the purple graph is going to give us a small positive answer minus a large positive answer gives us a negative answer, right?
Okay, what's that equivalent to?
Well, it's just interesting. I mean, that you can see what the math gods do for you here. I mean, by calculating, we could either do this separately, right? We did this separately, and we said we could add up the area under the white graph minus the area under the yellow graph gives us the area between the two, right? Which is easy to think of and see. But then if we combine both integrands into a new integrand, a new function, we get the same area defined under a different curve, right? I know that probably doesn't seem like that's anything super profound, but it really is. This is the kind of thing, like, for example, here's a really arcane example, like in string theory. When people try to this super advanced, topological approach to math, when they're trying to take these, there's only a handful of people in the world that can even truly understand this stuff. But they're trying to take all this mathematics from string theory and try to coax out the real world. Like, for example, they've been able to do things like say, okay, the math here, this is what represents gravity. And it works. It works, a lot of this stuff works well. But in order to do this stuff, they work in these 7-dimensional spaces called Calabi-Yau spaces, and they're just a subspace of the space of string theory, the 11-dimensional string space theory, string theory space. And what they've got to do is they've got to, like if they're talking about gravity as compared to electromagnetism, they've got to take these things and they've got to do these intense transformations to make them look like, all this really is, in a nutshell, is a simple example would be saying, like, topologically speaking, what's more similar? A drinking glass and a coffee cup. Compare those two things. Or a coffee cup and a hula hoop. Which two are more similar? coffee cup and a drinking glass, or a coffee cup and a hula hoop? Drinking glass and coffee cup, obviously, right? Not from the perspective of a string theorist. Because they're looking at this in terms of a topology. And what they're saying is, aha, coffee cup has a handle that has one open loop, right? You put your finger through when you drink it, right? Glass doesn't have that. A glass has a divot, but it's not open, right? It's closed. There are no loops in a drinking glass. There's a big loop, obviously, in a hula hoop, and so they're much more similar than the glass and the coffee cup. And so the whole point here is to transform mathematically, to make a transformation like saying, okay, we're going to move from a coffee cup into a hula hoop permutation. And one of those mathematically is going to be much better for dealing with a certain physical problem. The other one's going to be much better for dealing with a different physical problem. Trying to make these correlations. And it's kind of like this. It's like reconfiguring the area under a curve. Is it better to think of it as being a difference between two functions or an area under a completely different function? They mean the same thing in terms of the answer, right? The areas, if we look at the areas, they're going to be the same, but there are ramifications as to, if this is more involved, if we're talking about studying something that's not just abstract math, but maybe we're looking at something in terms of physics, where we're looking at the area under a work profile, force versus distance or something, force versus displacement. And then maybe the shape of what that area looks like is meaningful for us in trying to understand what's really going on physically. And so we might make these kinds of trades. Now this is this is a topic that's way out there. It's not something that you probably even deal with in any meaningful way your whole first year in college in math if you're studying math, but eventually you do. And so I just want you to start appreciating that there's something going on there, that when you apply these properties of definite integrals, that what you're doing is you actually are changing the shape of these curves, right? And even though it may not seem important now, it might be in the future, right? So anyway, just a little Monday topic. All right, ate up all your time, I think, didn't I, probably? Yeah, pretty much. Okay, so